All right, so the first thing we're going to do is go over the questions from last night's homework. We do this in every class, unless we have a quiz. Then we take the quiz first. So let us start with number 3. For all real numbers x, the square root of x squared is equal to x. So what you have to do is you have to write the negation of it. So what kind of statement is this? When it starts with for all, this is called a universal statement. Every universal statement has the form for all box, comma, oval, or triangle, whatever shape you want to put. So how do you negate that? So if this is statement P, how do you negate it? There exists box such that
Oval.
not oval. So square root of x squared is not equal to x. Did everybody get that?
Yeah.
Okay, good, you got 4 points. Okay, but now, then you have to state whether the original statement is true or false. Here's the original statement. For all real numbers x, the square root of x squared is equal to x. Now I know you guys see the answers on the bottom, but you guys gotta know. This is false. The square root of x squared is not equal to x. What do I have to change this to make it true?
Plus minus.
Boo! You were in my summer school class too. That's a double boo. Thank you. Absolute value of x. The square root of x squared is equal to the absolute value of x. Every year, students think it's x, it's plus or minus x. No and no. It's absolute value of x. This is kind of important in calculus. Absolute value of x. But just think about it. How can it be plus or minus? You're telling me the square root of 9 is plus or minus 3?
Yep.
No.
No, it's 3. Here, let me show you something. This is, I showed you guys this in summer school, but obviously we don't remember anyway. Let me show you something. Teachers skip an important step when they solve equations, and that's why students think certain things but which are not true. How would you go about solving this equation? Square root both sides. Okay. What is the square root of x squared? I just told you.
Absolute value of
Absolute value of x. What is the square root of 9? 3. It is not plus or minus 3. It's 3. And if the absolute value of x is equal to 3, then what is x? Plus or minus 3. This plus or minus is there because of the absolute value. But a lot of teachers leave out this step, and that's why a lot of students think the square root of x squared is x, and the square root of 9 is plus or minus 3, but that's 2 wrongs. Yeah, but Mr. Park, 2 wrongs made it right. Yeah, well maybe this time, but you're not going to get lucky every time. Okay, so that's an important one. That's why I want to make sure we go over it. And then number 6. No, number 5 now. Where's that 35? I forgot the comma. That's a strike right there. Number 5. Okay, so here's 5. For all real numbers a and b, the absolute value of a plus b is less than or equal to the absolute value plus the absolute of b. Okay, so again, what kind of statement is this? Universal. So every universal statement has the form for all box, comma, oval. So how do you negate that? So if this is statement Q, what would not Q be? There exists box, which is A and B are elements of the real numbers, such that not oval. So absolute value of A plus B is greater than the absolute value of A plus the absolute value of B, correct?
Yeah.
It's easy to negate it, but now, is the original statement true or false?
True.
How do you know? Because that's what it said on the bottom. Okay, you want to play that game? Okay. So on the quiz, what are you going to look at the bottom? What are you going to see on the quiz at the test on the bottom? Yeah, there's nothing there. You got to know, why is this true? In fact, this is a very famous inequality in mathematics. That's why I put it on there. Does anybody know what this is called? It's called the triangle inequality. If you go up into upper level mathematics in college, this is one of the things you need to do proofs in mathematics. The triangle inequality. Anyway, you could also figure it out just by plugging in numbers. Did you guys like plug in numbers? But you can't just plug in A and B are both positive. You gotta make sure you gotta try all the possibilities. One is negative, one is positive. They're both negative. And it works every time, doesn't it? But just because you plug in numbers, does that constitute a proof? No, that's not a proof, okay? But, like I told you, this is a very important thing when you do proofs in college. That's why I gave it to you. Number 6, oh, here's another one. This is another very important problem in mathematics. There exist natural numbers A, B, and C such that A cubed plus B cubed equals C cubed. So what kind of statement is this? Existential. So if this is statement R, what is the negation of that? Every existential statement has the same form. There exists box such that oval. How do you negate it? For all box, A, B, and C are elements of the natural numbers, comma, not oval. A cubed plus B cubed is not equal to C cubed. Everybody did that, right? So that's the easy part. Maybe this year we should make this the 2-pointer and then the true false 4 points. Let's switch the values. Take the challenge this year.
Next year.
Is the original statement true or false? 50-50 chance. Can you find at least one triplet of numbers A, B, and C, which are natural numbers, so that A cubed plus B cubed equals C cubed?
No.
Why? Okay, the answer, it is false, but somebody tell me why. Come on, impress me.
There's a triangle.
What triangle? What you talking about triangle? Come on, somebody impress me. Fermat's last theorem. You guys ever heard of this? Fermat's last theorem. Okay, Fermat was when did Fermat live? In the 1700s? I think the 1700s. Anyway, he was considered like one of the greatest mathematicians of his time. Anyway, this was a very famous problem in mathematics because if you have natural numbers, do there exist natural numbers A, B, and C such that A squared plus B squared equals C squared? Yeah, there are infinitely many, right? Because this is the Pythagorean theorem. Can you give me one triplet of numbers that satisfies this? Yeah, how about 3, 4, and 5, right? 3 squared plus 4 squared equals 5 squared, right? Pythagorean triples. Can you give me another? 5, 12, 13. Give me another. 8, 15, 17. Give me another. 7, 24, 25. Give me another. 9. Okay, very good. I taught you guys in summer school, yeah? 11, 60, 61. Now those of you who weren't in my summer school class, where did these come from? Come on, there's a pattern. When the first number is odd, there's a pattern. What is 3 squared?
9.
What do 4 and 5 have to do with 9?
Yeah.
Yeah, that's no. Yeah, I know. But what is 5 squared? What do 12 and 13 have to do with 25? No, that's just for you to wonder, yeah? What is 7 squared? What do 24 and 25 have to do with 49? The answer is dumb. So when the first number is odd, what? These two numbers add up to this one squared. They're consecutive numbers. So now, I give you this, 13. So what do you think in your head? 13 squared is 169. What consecutive integers add up to 169? 84, 85. That's how you can generate Pythagorean triples when the first one is odd. What happens when the first one is even? Well, what is 8 squared?
64.
What do 15 and 17 have to do with 64?
Half.
It adds up to half of it, and they're consecutive odd numbers, right? So, following that pattern, 12, what is 12 squared? 144. Half of that, 72. What consecutive odd numbers add up to 72? What?
Huh?
I heard something. What consecutive odd numbers add up to 72? What were you going to say? 71 and 1. 35 and 37. There's another Pythagorean triple. In fact, I like to use this on a test. Right there. And then, of course, you have some that just don't follow any pattern, like this. 20, 21. I gave this to you guys in summer school. Okay, if you don't know, then we just got to use Pythagorean theorem. This squared plus this squared equals that squared. What is that squared? 400 plus 441 is 841. What's the square root of 841?
29?
Very good. Come on, it's got to end in a 9 or a 1. But it's crazy to think it's 31, right?
Yeah.
You guys know why it's crazy? So somebody thinking, oh, I was guessing 30. No, because, okay, this is 400 plus 441, that's 841. What happens when you square root that?
Less than 50.
It's got to be less than 30 because 30 squared is 900. I don't think like that, Mr. Clark. Anyway, I'll tell you what. I love to use these on quizzes and tests. I'm just throwing it out there. So either you can remember your Pythagorean triples or you can just use the Pythagorean theorem and figure it out. Anyway, so we're backtracking here. So a squared plus b squared is c squared. There's an infinite number of triplets of numbers that follow that. But what happens when the power becomes bigger than 2, like 3 or 4? A to the 4th plus b to the 4th equals c to the 4th. Or 5, a to the 5th plus b to the 5th equals c to the 5th. Are there solutions for this? Well, for years, nobody knew. Nobody could figure it out. So that's why in Germany, they had a prize. This was called Vermas' last theorem. Okay? There was a prize. So some German person put up some money. They said, if anybody can solve this problem, I'll give you all this money. Okay? But nobody could solve it. So mathematicians for years and years, they tried to solve this problem, to figure out if this power is bigger than 2, are there solutions? But nobody could figure it out. But Fermat, he was one of the best mathematicians in the world at that time. But he didn't really want to bother with this kind of problem. But he wrote, in fact, he was sitting in his living room, and somebody brought up this problem, and he said, oh, the solution for this problem, I have the solution to this problem, but the margins of this book are too small to hold it. That's what he wrote in the book, and that was it. So people thought for years that he actually had the solution, but then we don't know because he died after that. So this problem has been going on for years.
Oh.
Finally, in 1991, which is not that long ago, did you guys ever hear of Andrew Wiles?
You graduated from Yale.
Apparently not. Andrew Wiles, look, I even got his autograph here. See? Andrew Wiles? Where's his autograph? Oh, right there. Anyway, a former student of mine went to Stanford, and this guy did he did a lecture on, he actually proved that theorem, so he autographed it right there. Because if you could prove this theorem, you would be the most famous mathematician in the world. So in 1991, Andrew Wiles thought he solved the problem. Because when he was a little kid, he thought his goal in life was to solve this problem. That's what he did. So he went, I believe he was a professor at Princeton, so he would do his work in the day, and then he would go home at night, and he would just work on this problem until he fell asleep. Every day, for years and years and years. And then in 1991, he thought he had the answer, so you know what he did? He gave a lecture series. It was like over 4 days, I think. First day, second day, third day, and then on the 4th day, it was all leading up to this, and he put it on the board, and then what do you do when you finish a proof? What do you write? And don't say happy face. What do you write when you finish a proof? Q-E-D. Quod erat demonstrandum. Who takes Latin here? Quod erat demonstrandum, what does that mean?
Or no, which was great.
No, that which was to be demonstrated. Anyway, and then everybody gave him a standing ovation because nobody could solve this problem for years. But in order for this to be true, see, he claimed that he actually proved it, but it had to be checked. But the problem was there's only like 5 mathematicians in the whole world that even understood this proof. So they had to go through the proof, and you know what happened? There was something wrong with it.
No.
So he actually didn't prove it. So what happens is he kind of went into a depression, and then one day he was walking along the river, and then he said he had an epiphany, and so finally in 1993, he actually did the proof, and it was checked, and it was correct. So once he did that proof, he was the most famous mathematician in the world. That's why all he did is he went across the United States and the world, and he gave like a 1 minute, 1 hour lecture, and you know what? He got like, I think he made 100,000, no, that can't be true, but $10,000? Is that?
What's it?
Yeah, for an hour, you make $10,000.
Oh.
Isn't that pretty good?
Did
Yeah.
you win that German money?
Yeah, and he got the money too. I mean, I don't know exactly what it was. You guys can look it up. Just Google Andrew Wiles. Anyway, some of you might be taking multivariable calculus, yeah? When you're a senior.
No.
Like if you're not in 11th grade or not, if you're like 10th or 9th grade. Anyway, multivariable calculus, we actually watched a video of this. It's called A Proof. Now, some of you might think I'm ranting, but who knows, one of this might actually appear on Monday's quiz. That's what I like to do, you know. You'll find out soon. All right, next problem. Enough ranting and raving about that. Okay, what's the next number? I thought we were going to finish this early. 6, 9. Oh, there you go. Here's another important fact. Every even number greater than 2 is equal to the sum of 2 prime numbers. Now, you guys understand that statement? Every even number greater than 2, like 4, 6, 8, 10, 12, is equal to the sum of 2 prime numbers. Now, first thing, let's negate that. What kind of statement is that? It says every.
That's a universal.
That's universal. So, how do you negate a universal? Existential. So, there exists an even number greater than 2 that is not equal to the sum of 2 prime numbers, right?
Yeah.
Okay, that's easy to do.
One of them.
Okay, or you can just say some. Some even numbers greater than 2 are not equal to the sum of 2 prime numbers. But here's the most important part. Is that original statement true or false? Every even number greater than 2, so here 4, is that equal to the sum of 2 prime numbers? You know what somebody said last year? 1 plus 3?
Oh, I almost said.
1 is not a prime number. If 1 was a prime number, all of mathematics would break down. Yes, it's true. Okay, 2 plus 2. Okay, what about 6? Is that equal to the sum of 2 prime numbers?
Yeah.
Yeah.
What? 3 plus 3. What about 8? 3 plus 5. Obviously, you guys put a lot of thought in this, yeah? 10. 5 plus 5, or 3 plus 7. So every even number greater than 2 is equal to the sum of 2 prime numbers. Well, it worked for these 4, therefore it works for all.
Yeah.
No, that is not. It was sunny the last 3 days, therefore tomorrow will be sunny. Hey, wait, why am I writing on this side of the board when we're videotaping?
Erase.
So that means whatever I did on that side of the board, the people, they're not going to even know what I was talking about. Did I do stuff on this side of the board?
Barely.
Okay, good.
Just that.
Okay, good. Okay. Okay, so is the original statement true or false? This is a trick question.
It's not solved.
So it worked for the first 4, therefore it works for all. No, that is not a mathematical proof. When you prove something, you have to prove something that it works for everything. Okay, by the way, this is a very famous problem in mathematics. That's why I put it up here, to expose you to these things. Okay, this is called gold box conjecture. You guys ever heard of that? What do you guys do in elementary school? Go to recess? Play in the park? Or you stay in the classroom and read about mathematical things like this? Goldbach's conjecture, named after the mathematician Christian Goldbach, his conjecture was this: every even number greater than 2 is equal to the sum of 2 prime numbers. Now the thing is, it's called a conjecture. You know why? Because it hasn't been proven yet. Right now, this is one of the most famous problems. If you can prove it, you're going to be super famous and you can make probably now $20,000 for a 1-hour lecture. So if you can prove this. So, this hasn't been proven yet, so what's the answer? What does it say on the bottom?
Question mark.
Yeah, we don't know. The answer is we don't know if it's true or false because it's just a conjecture. It has been neither proven nor disproven. In fact, you know what's a funny thing? Somebody actually proved in mathematics that in mathematics, some statements cannot be proved true or false. Somebody actually proved that. Think about that. In mathematics, there are some statements that cannot be proven true or false. Somebody actually proved that. And you know what his name was? Kirk Gödel. See, when you have the O, that's pronounced Gödel. It's called the incompleteness theorem. You guys ever heard of these things before? What do you do in elementary school? Did you guys at least watch Donald Duck in Mathemagic Land then?
Yeah.
One for two people, that's it? That's why in this class, when we have extended periods, we're gonna watch Donald Duck in Mathemagic Land.
Alright.
See, because what you're supposed to do is your parents put you in front of the TV, show it to you when you're like 3 or 4 years old, and you gain something from it. And then when you're in elementary school, sometime you watch it again, and then you, wow, I didn't know that was there. And then when you come to high school, then you watch it again, and you learn it, you see it at a different level. But some of you guys didn't do what you're supposed to do when you're as a kid. What did you guys watch as a kid on TV? Like Lion King.
Between the lines.
Look, Lion King is good, it's Disney, but so is Donald Duck in Mathemagic Land. But who gets to watch out? But isn't that kind of perplexing? Somebody actually proved that there are some statements in math that cannot be proven true or false. It's quite awesome.
How do you do that?
All right. Okay, did we go over all? No, number 10. Oh, I wouldn't be surprised if we saw number 10 on Monday's quiz. But in fact, you know when I say things like that, you know what you should do? You should like put a circle around it. I'm going to study them. But it's up to you. For all real numbers x, comma, there exists a real number y such that x times y equals 1. Okay, so this is statement P, negated. Now, what kind of statement is this? See, this is a more complex problem where you have to kind of extend what you know, but if you just do what I told you to do, it's easy because this is a universal statement. For all box, comma, oval. Just follow the form. How do you negate that? There exists box such that not oval. Now, what's in the oval? It's an existential statement. How do you negate that? It's a universal statement. So how do you negate this? Just follow what you know. For all box. So inside here you got there exists box such that oval. How do I negate that? For all box, comma, not oval. X times y is not equal to 1. Did you guys get that at least? Okay, now is the original statement true or false? For every real number x, there exists a real number y, so that when you multiply them together, you will get 1. Okay, let's try. Think of a real number. 2. Is there another real number so that when I multiply it together, you get 1?
Yeah.
Yeah, half. Okay, what about 3/4? What can I multiply it by to get 1?
4/3.
So I can think of any real number. I can find another real number to multiply it by to get 1 every time.
That's what it says.
No. The answer is false. Somebody give me the counterexample.
0.
0. What do I multiply 0 by to get 1? And don't say
Undefined.
1 over 0. Cancel out the zeros. No can. So that's why it's false. So you gotta think. This is a thinking class, people. You guys don't like to think, yeah? But that's what mathematics is. Mathematics is thinking. How come you guys don't like? And I also noticed that nobody put any problems past number 10.
The truth table?
Yeah, the truth. Yes, you could do the truth tables, but did you learn from them?
Yeah.
Yeah.
Okay, we'll see. We'll see if you learn. I'll be the judge of that.
Hopefully. Oh, the negation of P.
I'll be the judge of
P
that.
or Q is the same as the.
Now, when I write problems, I don't write problems just so you do busy work. I write problems so that you're gonna learn something. Okay, so number 11. This is what you're supposed to learn from number 11. Not P or Q. Okay, now everybody did the truth table because nobody had a question. Now let me just do it in my head. That one's easy, right? Because it's just gonna be false, 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 true, correct?
Yeah.
Okay, and then you make a truth table for number 12, which is not P and not Q. Let me do that in my head. Whoop! False, 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 true. Did everybody get that?
Yeah.
Hey! Those truth tables are the same.
They're logically.
There must be
equivalent.
there must be something with that. Well, if you read the notes, if two statements have exactly the same truth table, then we say that these statements are
Logically.
logically equivalent. This is super important in logic. So anytime you have two statements that have exactly the same truth table, we say that they're logically equivalent. Notice that it kind of looks like an equal sign, but only numbers can be equal. These are statements. Statements are logically equivalent. Just like negation, doesn't that kind of look like a negative sign? A little bit? But see, you have a number, and then you have its opposite, right? You have a statement, and then you have its negation. Actually, this should be not P. Yep. You see the difference? It's kind of similar in meaning, but this one deals with numbers, this one deals with statements. That's the difference right there. Oh, so Mr. Park, I did number 13 and number 14. They have the same truth table. So what did you learn from number 13 and 14?
They're also logically equivalent.
Yeah, so the negation of P or Q is logically equivalent to not P and not Q. You see these two things here? This is kind of important. We call these De Morgan's laws. Doesn't this kind of remind you of something? Doesn't that kind of remind you of the distributive property?
Yeah.
So, if you have a negation sign outside either an or an and statement, you can actually distribute it, but
Reverse.
you have to change the or to and or the and to or. That's why some logic books actually call these the laws of distribution. That's because it's like the distributive property. So when you do your homework tonight, okay, it's going to be the same thing. When you see things that have the same truth table, you got to be thinking, oh, those are logically equivalent. Because by the time we take the test, which is coming up kind of fast, one of the most important things is to know what statements are logically equivalent to the others. Otherwise, no can. And then what about 15 and 16? I'm not going to write it on the board, but I will. P or Q and R. So did everybody? Yes, you guys did. You made the truth table for that. And then P or Q and P or R. So you did both of these truth tables and whoa, they came out the same. So what can you conclude? They're logically equivalent. Now, we didn't do this on the homework, but if you look at the form, let me just ask you. If you had to guess what is logically equivalent to this, what would you guess? Following the form that you see here. P and Q or P and R. Now, we haven't proven it yet. Like, what if on next Monday's quiz, what if I tell you to prove this? What would you do? Make a truth table for this, make a truth table for that, and show that they're exactly the same. That's what you would do. That's how you prove that statements are logically equivalent. They have exactly the same truth table. Okay, now we are done with this. What about the log one? Every year everybody can do the log one. Every year that comes up. So this year is special. You guys are special then. Everybody remembers logarithms.
Yeah.
Okay, good.
Not really. It's almost
What about did I give you a trig one yesterday? No, here, I want to test you. Let's just see how good you are. I want to see so if you guys remember logarithms, then the probability is quite high you remember trigonometry. For all real numbers x and y, comma, cosine of x plus y is equal to cosine x plus cosine y.
Oh, totally.
Okay, is this statement true or false?
False.
Can I just distribute the cosine?
No.
No, that's ridiculous. In fact, in mathematics, most of the time you can't distribute. Okay, so what do I need to change that to make it true?
Sine.
Come on, I know you guys learned
Wait,
this
is
last
it
year.
cosine?
Cosine x,
Sine.
cosine y,
Minus sine.
minus or plus?
Minus.
50-50 chance.
Yeah.
Minus sine x, sine y. Boom! Does that look familiar?
Yes.
Yeah.
Oh boy. Well, how come you could remember logarithms but not this then?
Beginning.
Because we did logarithms in SAT prep. Well, we also did it, but we didn't do this identity. Don't worry, you don't have to be responsible for this identity until we get to trigonometry. But you should know that it's false though. You should know that you can't just distribute the cosine, right? That's what I expect. You might not remember the correct identity, but you gotta know that you just can't distribute the cosine. That's a fatal error. Okay, what are we doing today? Well, we're gonna look at more statements. Okay, the first one is called a conditional statement. Oh my gosh, we're running out of time. We're in trouble.
Yeah, 20.
You guys know what a conditional statement is?
It's
If
a
then,
condition.
Very good. A conditional statement looks like this. If P, then Q. Now, usually theorems in mathematics are stated as a conditional statement, like for example in geometry. If two parallel lines are cut by a third line, then the alternate interior angles are equal. Remember that from geometry? So normally theorems are stated as conditional statements. Okay? So, if P then Q, but see the thing is, we like to symbolize. So this is how we symbolize the conditional statement. So when you see this, you think if P, then Q. Now, unfortunately for you, there's other ways of saying it. This is the most common way, but there's other ways like P, this is all in your notes by the way, implies Q. Does that make sense? If P, then Q. P implies Q. What's another way?
Q with P.
P
Only if.
only if Q. Q if P. P is a sufficient, why am I writing this all down when it's in your note? Condition
is
For Q. Q is a necessary condition for P. All of these mean the same thing. P implies Q. Do we have to know them? Well, we'll find out, won't we? Why do I have it in the notes then? Well, of course, if you're on the math team, you gotta know it, right?
Yeah.
Chang, Kid?
Yeah.
Were you at Me Too last year? You had to learn logic? Yeah, you gotta know this. You gotta know it all. Okay, now what about the truth table? Oh, no, we can't do the truth table yet. Now, if you have a conditional statement like this, you can form other statements. Now, I looked in your geometry worksheets, and you know what? It was there. So this is called a conditional statement, right? But we can form other statements. One is called,
The contrapositive.
okay, but we'll save that one for last. What are the other two? Oh, the converse. What is the converse of if P then Q? I'd rather say P implies Q.
If Q.
Q implies P. You simply just switch the two. Oh, by the way, when you have a conditional statement, what is that part called? It's in the notes.
The P.
No. But what if it's not P? What if it's like A implies B? Is this called the hypothesis? This is called?
Conclusion.
Let's see, the notes has it all. So, to form the converse of a conditional statement, you just reverse the hypothesis and the conclusion. It's quite simple. What about the inverse? How do you form the inverse of a conditional statement? Not P implies not Q. And then let's do the last one. It's called the contrapositive. What is the contrapositive of P implies Q?
Not Q.
Not Q implies not P. There you go. So tonight's homework, see look, I give you a conditional statement, you have to form the inverse, the contrapositive, the converse. I'm not gonna even talk about the negation, because you gotta learn. See, when you're making truth tables for these things up here, you gotta learn from them. That's why I write problems. So when you do number one, you're gonna learn something so that you can do number two. You don't like that kind?
No.
But that's what math is.
I'm not
You build up tools. That's what I'm trying to do. I'm trying to put tools in your tool belt so when you see a problem, then you take out the proper tool. But some of you, all you have is like a tiny hammer and that's all you can do. What if you have to turn the screw? How you can turn the screw with a tiny hammer? The more tools you have, the more efficiently you can solve problems. That's what this is. It's all problem solving in this class. I'm giving you tools, and then you have to learn to take out the proper tools to solve the problem. And if you go through this entire course and you just insisting on using the tiny hammer, then you're just going to have a headache at the end. Okay, how do I make the truth table for the conditional statement? So here's P and Q. So what did we learn from yesterday? When you have two statements like this, how many possibilities are there?
4.
4. So what's the conventional way to do it?
T.
True, true, false, false, true, false, true. So everybody's on board with that. So yesterday we did and or. Today we do the conditional statement, if P then Q. You know what, let me just, in the interest of time, let me just tell you. It's true, false, true, true. That's the truth table for if P then Q. Now I want you to notice something. The only time a conditional statement is false is when the first part is true and the second part is false. That's the only time it's false. And let me tell you something here to help you understand this. Okay? What if I told you, if you do your homework, then I will pay you $10. If you do your homework, then I will pay you $10. So what would happen if you did your homework and then I paid you $10? Am I a liar?
No.
No. What if you did your homework and I didn't pay you the $10? Am I a liar?
Yeah.
Yeah, see, false. What if you didn't do your homework but I paid you $10? Am I a liar? No, I'm just
No.
stupid, right? I'm just stupid, but I'm not a liar. What if you didn't do your homework and I didn't pay you $10? Am I a liar? No, see, the only time I lied was that one. Does that help?
Yeah.
Okay, if it doesn't help, then just memorize. The only time a conditional statement is false is when the first one is true and the second one is false. That's the easiest thing to remember. Now, if we have a conditional statement, then there must be a biconditional statement. And if a conditional statement is written like this, then what do you think the symbolization for the biconditional is?
2 arrows.
Yeah, it goes both ways. Like that. That's called the biconditional statement. And when we see the symbol, how do you read it? P, if, and only if Q. See, that's like putting these two together. You put these together, then you get if and. Or some books are actually read it like this. They put the if with. No, if you read math books, do you guys even read math books? What's a math book? You ever saw this before? An if with the 2 F's? Some of you probably thought, oh, that's a misprint. No, it means if and only if. That's what it means. It's a biconditional state. Also, you know what other ways of writing this? This is in your notes. P is a sufficient and necessary condition for Q. It's like putting both of these together. It's all in your notes, people. Okay, now, what does the truth table look like for the biconditional statement?
True, false, false.
And in the interest of time, I'll just tell you, true, false, false, true. So how do we remember this? Well,
Yeah.
this is when it's
Same.
true, this case and this case, so how can we do that?
Same.
Yeah, when they're both the same, both true or both false, then the biconditional statement is true. But if they're different, then it's false. So these are all the truth tables that you need to know. You don't have to know anymore. So all you gotta know is not, and, or, conditional, and biconditional. That's all you gotta know. And then from those 5, we're gonna derive everything else. That's what you're gonna do in your homework, yeah.
What's not? That doesn't.
Not is this one, you know, like this.
Okay. That's just
Okay.
switching it.
Too late, I'm gonna do it already. You ask for it, you're gonna get it. So when you just have one statement, there's only 2 possibilities. It's either true or false. You guys remember this from yesterday?
Yeah.
So if P is true, what is the negation of it? False. If it's false, then it's true. There you go.
Alright.
That's the truth table for negation. Okay, so what do you think you're gonna do tonight? You're gonna make truth tables. Okay, however, you gotta learn from it. In fact, should I do one for you?
Yeah.
Okay, I will do C. Yeah, that's okay, I will do it. See, but this is the kind of stuff you gotta learn from. Construct the truth table for not Q implies not P. So, shall we make the training wheels, or you can do it in your head? Okay, training wheels. P and Q. P is true, true, false, false. Q is true, false, true, false. Correct? So,
Yeah.
if P is true, true, false, false, what is not P?
False.
False, false, true, true. And then what is not Q? False, true, false, true. And then you gotta connect these two with the conditional statement. Now again, when you have a conditional statement, when is the only time it's false?
First one's
When
true.
When the
either
first one is
false.
true and the second one is false. So right there. In every other case, it's true. So this right there represents not Q implies not P.
Isn't that the contrapositive?
Wait, so.
So what did I just
This-
learn from that
yeah,
problem?
which
What
is
did I just
happening?
learn?
Which is
P implies Q is
Okay.
logically.
What was okay? So some of you are going, what are you talking about? What did I just learn?
Yeah, I almost.
Well, what was the truth table for P implies Q?
TF.
True, false, true, true. Hey, that's the same thing. If two statements have exactly the same truth table, then what? They are logically equivalent. So what did you just learn from this problem? P implies Q is logically equivalent to
Then you
not Q implies not P. In fact, if I just had to teach you a teacher could only teach you one thing in logic to before you go out into the world, this would be it right here. Any conditional statement is logically equivalent to its contrapositive. In fact, they tested you on this on the PSAT, you know. 2 years ago on the PSAT, they gave an if-then statement and then they asked, which of the following is equivalent to it? And if you knew this, you just pick it up and you're on your way. But if you didn't know it, then you just 1 out of 4 chance. Yeah.
The rule for this one with like one arrow, what's that called again? The
Conditional.
Conditional is if they're different, then it's.
No, time out. The only time it's false is when the first one is true and the second
Okay.
one is false. Yeah. That's the biconditional is when they're both the same, it's true. If they're different, then it's false. Okay, so tonight make truth tables, but when you make the truth table, you gotta make sure look for logically equivalent things, because if you look in your notes, I give you a list of logically equivalent things, but then I want you to discover it on your own. Now, the last thing we have to learn. Now, why do we study logic? Just so teachers have jobs.
So, yep.
Who said yes? That's strike one. No, almost everything in mathematics has an application. And there you go. This is the application of logic.
Ooh, logic gates.
Yeah. Exactly. Logic gates, electrical engineering. That's right. That's why, you know, one of my friends is a PhD in electrical engineering, and then he came to visit me one day, and it happened to be in a PCH class, and in front of everybody I asked him, well, so, what were the 2 most important things in high school mathematics you have to know to do engineering? And you know what he said? Logic and imaginary numbers. That's what
Right.
you gotta know for your life. Because that's what it is. All of engineering is logic and imaginary numbers. So how can we apply this to electrical engineering? Well, every statement in logic is either true or false. So like in real life, do we have situations that have only 2 things? Yeah.
This
If you
one's
have a
false.
wire, either current is flowing through it or it's not. It's either turned on or turned off, right? Like, did you guys, so like if it's turned on, we call that 1. 1 is like true, or 0, off is like false. In fact, if you look at your computer, you know your on-off switch? You guys even
Oh,
have
yeah.
computers? Doesn't
Yeah.
the on-off switch look like that?
Yeah.
On, off.
And when you can
No,
bind
mine
it.
says on and off
Yeah,
is
they
the
go
part.
together.
Yeah.
Whatever, okay? So, we can apply logic directly to this. So, what we have is, you have a network that looks like that, and then we have what we call these gates, logic gates. Now, there are 3 logic gates. The first one is not. So, let's say you have something like this. That's not. Not is negation. It works exactly like negation. So, if the input is a 1, or you can think of it as true if you want, but when you do electrical engineering, you think 1. What do you think the output's going to be?
Zero.
Yeah, it negates it. It goes from 1 to 0. What if the input is a 0?
1.
Then the output is 1. It negates it. So it's called the NOT gate. Okay, then we also have the AND gate and the OR gate. Okay, the AND gate looks like this. You have 2 inputs and then this thing coming out here. Because when you have an AND statement, don't you have to have 2 things? Like this P and Q, you have to have 2 things, right? So, it works exactly like the AND statement. What if this is a 1 and this is a 1? What do you think the output's going to be? If you have true and true, it's gonna be true, right? What if you had this? What's the output gonna be? If one is true and one is false,
Zero.
then it's false. It works exactly like AND. So you just gotta remember, one is true and 0 is false. Now the OR gate looks like this. So what if this is a 1 and this is a 0?
One.
Very good, because how does the OR statement work? Is at least one of them true?
Yeah.
Yeah, so then it's true. What if both of them are 0?
Then
Then what's the
zero.
output gonna be? It's gonna be 0, that's right. It works exactly like the OR statement. Now, just based on these three, we can figure out, we can build everything else. So what's gonna happen by the time we get to the test is you're gonna be the engineer. Right now, see, you guys are in the embryo stage yet, yeah? So slowly, you're gonna like grow in the womb, emerge from the womb, and then you're gonna start walking. That's what you guys are gonna do. And hopefully you do that by the test, because if you don't start walking by the test, you're in trouble. You know what I'm talking about? So what's gonna happen is, I'm gonna give you like this, P and Q. I'll tell you exactly, this is the exact problem.
On the quiz?
No, on the test,
Oh, I figured.
I'm gonna give you this, so here's P, here's Q. Using these gates, you have to design something so that the output is, okay, I'll give you a simple one now. 0, 0, 0, 1. Using just these three things here, can you design a network so that this is the output right here?
No.
And the answer is yes, you can. If not, you get -8. That's how it works, people, I'm sorry.
You do or not.
Okay, so this is what you should do. This is what you should be thinking. Is this something I know? Do I know anything right now that's false, 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 true? Look, we only have 5 truth tables that we learned. Is any of them false, 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 true?
Yes.
No. The answer is no. So then you think, okay, what about the negation of it? True, 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 false. Do we know anything that's true, true,
Or.
true, false?
Yeah.
Yeah, that's the OR statement. So isn't this simply the negation of the OR statement? Yeah. So that's how you, so this is, okay, so this is P or Q, right? This is simply the negation of it then. So all you have to do then is, you have P and Q, you OR it, and then you negate it. There you go, you're the engineer. But of course, that would be a little too simple for the test, yeah?
That's simple.
Why would I give you something this simple on a test? My dog could do that. But somebody, see, the thing is, every time I put this on the test, people come up with like creative ways. Like somebody might say, "Oh, Mr. Park taught me that I can distribute the negation sign." Remember, we learned this about 30 minutes ago. Isn't this the same thing as not P and not Q? Remember De Morgan's law?
Yeah.
Who's De Morgan? So instead of this, you could build that then instead, because they're logically equivalent. So what you can do is P gets negated, Q gets negated, and then both of these get put together with AND. Boom! That does the same thing. However, if I grade you on efficiency, both of these work. But in real life, every time you put one of these in a circuit, it costs money, yeah? So which one, if you're the engineer, and you're building something, and you're presenting it to your client,